Hello class, welcome to Geometry Lesson 11.2, Prisms and Cylinders. So our central question of the day is, how does the volume of a prism or cylinder relate to a cross-section parallel to its base? In addition, we want to use the properties of prisms and cylinders to calculate their volumes and surface areas. We also want to address the question, how can the surface area of a prism or cylinder be calculated? So this is going to be our focus, is to do volume and surface area of these shapes. So first off, we're going to look at Cavalieris Principle. This principle states that if two three-dimensional figures have the same height at each level and the same cross-sectional area at each level or each slice at every point in the height, then they have the same volume. So as you can see in this image, you have these three shapes, and when you make this horizontal slice, and you look at the cross sections from those slices. So you have here a square for this prism, rectangular prism. You have a triangle for this triangular prism, and you have a circle for this cylinder. When you make those slices, if those slices or cross sections have the same area, so we're assuming that these areas are the same, and this is the case for every single slice that you do vertically. So for example, if I were to slice it here, I would get the same exact cross sections. Then if that's true and the heights for each of the shapes are the same, then that means the volumes must be equal, since the cross-sectional areas are equal and the height is the same. All right, so here's an example. We can use Cavalieris Principle for shapes with different cross-sections shapes, but we can also apply it to those with similar shapes. So for example, we have a right cylinder and we have an oblique cylinder. They have the same height, and if we were to make draw the cross sections, they would both be circles with the same dimensions, and therefore the circles have the same area, and therefore with the same height, and therefore the cylinders have to be the same volume. Now if you were to, so that would be an example of the Cavalieris Principle. Now if you were to apply it to something like this, well, if I were to make this slice amongst all of these, for example, then the cylinder and the oblique cylinder will obviously be the same. However, if I were to do it with the cone, notice that the cone, the circle for the cone actually gets smaller as you go up. So if I keep making these slices, the circle gets smaller, and therefore the area of the cross section for the cone is not the same as the cylinder and the oblique cylinder, and therefore the volume of the cone is not the same as the volume of the cylinders, even though the height is the same, because of these cross-sectional area changes. So that would be a non-example of Cavalieris Principle. So in this case, the volume is not the same. It is not the same as the volume of the cylinders. All right, so I liken the Cavalieris Principle to a stack of pancakes, or maybe like a stack of index cards or something. On the left, we have a stack of pancakes that is straight up, and you can kind of think of it as a cylinder with those circular slices stacking up to make the cylinder. So that has a certain volume. Now if I take the same stack of pancakes, 3 pancakes here, assuming that the pancakes are the same radius, right, the same cross-sectional areas, then here I have an oblique cylinder. And so this oblique cylinder, assuming that it has the same height as the first stack of pancakes, and the cross-sectional areas are the same, the pancake slices are the same area, then that must mean that the volumes have to be equal. Now, applying this to the index card, so let's say we're looking at a prism, a right prism, as opposed to an oblique prism, the same idea holds. Assuming that I have the same amount of slices, essentially meaning the same height for both stacks, it doesn't matter if they're rearranged in this order where it looks oblique or not. The volume will still be constant. All right, so the volume of the cylinders and prisms, let's go ahead and take a look at the stack of pancakes that we looked at earlier. Now the volume of a cylinder or a prism is given by BH, where B is the cross-sectional area, so of the base, right? So it's the area of the base, essentially. So so the area of the circle, we know, is pi r squared. All we need is the radius for the circle. And so capital B can be replaced with pi r squared, and then times the height of the stack. So in this case, if I'm looking at 3 pancakes, then that's based on the height, right? If I have this bigger stack of pancakes, then obviously the height will be bigger, and this h would be larger. So think about it as in terms of you're calculating the area of each slice here, and then you're counting the how high the stack is, and that gives you the total volume. Now for the prism, for the stack of books here, you can think of it, if it was stacked up straight, then you can imagine that this would be some kind of prism, right? And we can find the volume of such. So if we know that using the same formula, that the capital B is this base here, which is a rectangle, which is the top surface of this book, or the top surface of this bottom book, regardless. And that will be your capital B. And then we know that the dimensions of that top surface is just literally it's just the base times the height. And so you take the base times the height, and then times the height of the prism, and that gives you the volume. All right, so the volume of the cylinder and prism, for the prism, we know it's capital B times H, where this is the cross-sectional area, which is dependent on this base area here. And I usually use capital H for this. So we can distinguish it from regular H for the cross-section of the rectangle. For example, this rectangle represented by this capital B is base times height. And the volume of the cylinder, again, I use capital H here. I like to use capital H instead of lowercase h. But it's the base area for this circle, which is pi r squared, times the height of the cylinder. So let's go ahead and apply this to the first example. Find the volume of each prism or cylinder. Now we know that this is oblique. However, by Cavalieris Principle, we can still apply it to a right cylinder or any cylinder of that dimension. So we know that the volume of a cylinder is pi r squared h. And we know that the radius is 5, so it's going to be 5 squared. And then the height is 8. And we're assuming that these are both in centimeters here, not in meters. So we have 8 centimeters and 5 centimeters. And so we got 20, so 5 squared is 25, and then you got 25 times 8, which we'll do on the calculator here. You get 200, so you get 200 pi. And this is going to be in centimeters cubed. Remember, volume is always in cubic units. Area is always in squared units. And of course, you can put this in the calculator and get a decimal out of this. Now for part B, we have a kite prism. Notice that the base is a kite, right? So we're looking at this bottom base here, that's a kite. And so the area of a kite is actually equal to the length times the width divided by 2. So, or the length times the height, I guess you can say. We'll call it the length times the height divided by 2. So if you look at any kite, right, you have this width, this length here rather, and then this height. And then this is like its length. So I multiply those and then I divide it by 2, and that gives me the area of that kite. So let's go ahead and do that. We know that the length here this is 4, so that means this has to be 4. So this length is 8 for this kite. So that's 8 right there. And the height is 12. 2 plus 10. So we got 8 times 12 divided by 2, which is 6 times 8. And we're going to call this capital B, remember, because capital B is the cross-sectional area. So we have 6 times 8 is 48. All right, so this is going to be 48 inches squared. Now the volume of this prism is capital B times capital H. And we know capital B was 48 for the kite. So 48 inches squared times the height of the prism, that's going to be the 5 inches. So we got 5 inches. We got 48 times 5 is 240 inches cubed. And that's how you find the volume of this kite prism. All right, so let's find the volume of the following prism. This is notice that the base here is a hexagon. So this is a hexagonal prism. So let's go ahead and find the area of this hexagon, they have to give us one of the dimensions. So in here, the dimension of the dimensions of one of the sides is 6 inches here, and it did not give us the height. So let's go ahead and provide the height here. The height should be 8 inches. All right, so we got this prism in which we have a regular hexagon. We know one of the sides, but actually we know all the sides because it's regular. It's a regular hexagon, symmetric and all that. So how would we find the volume of this prism? Well, remember that the volume is capital B times capital H, the base area times the height of the prism. And in order to find the base area, let's go ahead and look at that hexagon. And we know that the sides are 6 inches each. So in order to do this, what we're going to do is we're going to start from the middle, and we're going to basically draw out a bunch of triangles here. So notice that I can form 1, 2, 3, 4, 5, 6 of these triangles. And so I'm going to do I'm going to focus on one of these triangles and then find the area and then times it by 6, because I have 6 triangles that I can get from this hexagon. All right, so let's show you how to find the area of this hexagon. Now we know that this is 6 inches here for this side. So we also know that this angle here has to be 60 degrees, because if we have 6 triangles, well then 360 divided by 6 is 60. So we know that this angle has to be 60 degrees. We also know, and I'll draw this a little bit bigger here. So let me draw this a little bigger. Okay, so we got this is 60. We also know that we can break this up like this so that it's a right angle, so that we can form a right triangle. So essentially this 60-degree angle is now going to turn into a 30-degree angle for this little right triangle here. And if that's 30, then this has to be a 60-degree angle. Okay, so we got a 30, 60, 90 triangle. And that's a special type of right triangle. And if this is 6 here, if this whole thing is 6, then that means that if this is 6, then this has to be 3. So let's focus on that part. So if that's 3, then we should be able to find all the sides for this 30, 60, 90 triangle. Remember that in a 30, 60, 90 triangle, the sides are given by x, square root of 3, and 2x. So if I know the shortest side, then the hypotenuse is double. And if I know the shortest side, then the second longest side, or the second longest is that side times square root of 3. So if I know this is 3, then I know that this is 3 square root of 3. And then I know that this is, if that's 3, then this has to be 6. All right, so now we could find the area of this big triangle, of this entire triangle. Let's change the color here. We can find the area of this big triangle, because the area of a triangle is 1/2 base times height. So it's going to be 1/2, the base is 6, times the height, which is 3 square root of 3. So now that we know what the height is. All right, so we have that the area of the triangle is 1/2 of 6 is 3. 3 times 3 is 9. So this is going to be 9 square root of 3. Okay, so now we got the area of that one triangle. Let me go ahead and erase all this here. And that was 8 inches. Okay, so now that we got the area of that one triangle, then that means we can get the base area, capital B. Capital B is 6 of those triangles. So it's going to be 6 times 9 square root of 3. All right, so it's going to be 54 times the square root of 3 is the area of that hexagon. Okay, so that was, I showed you a trick for finding the area of a hexagon, and you can apply this to any type of polygon like this. If you have a heptagon or some other shape, you just draw the number of triangles and use this trick. So now we do this. So now we got, this is 54 times square root of 3. And then we multiply by the height, which is 8 inches, to get our volume of our prism. we get 432 times square root of 3. And this is going to be inches cubed. All right, so now let's look at the surface area of a cylinder. So the surface area of any solid is the sum of the areas of each of its faces. So in this case, for the cylinder, you have this base here, which is a circle. You have this base here, which is also a circle. And then you have the face, which surrounds the entire cylinder, which is this in red. Okay, so in order to get the surface area, well, we have two circles, so that means it's going to be 2 pi r. There's going to be this area of a circle is pi r squared, and you have two of those circles, so it's going to be 2 pi r squared. Now for the circular part, notice that this circular part is actually a rectangle if unwrapped. If I unwrap that rectangle, that label for the, let's say, a can of baked beans, you take that label and you unwrap it, then it's just a rectangle. And this rectangle has to wrap around the entire cylinder. So that means you have to wrap around the circumference. And the circumference of a circle is 2 pi times the radius. So that means the length of this label has to be at minimum the circumference of the circle in order to surround it. And then the height has to be the height of the cylinder, which I'll call capital H here. All right, so that means that the area of this rectangle is 2 pi r times h. So let's go ahead and provide the formula. The right cylinder is two circles, 2 pi r squared plus 2 pi r h. 2 pi r h comes from here. All right, so now let's take a look at the oblique cylinder. Now for the oblique cylinder, you also have two circles, so it's going to be 2 pi r squared. However, for this part right here, this label part, you're also going to have a rectangle. However, the length of that rectangle, the dimensions of that rectangle will change, because now instead of looking at the height, you're actually concerned with this slant height, which this dimension right here, which I'll indicate in blue, which is your slant height, your slant length. So that dimension is going to be represented by the height of this paper. So this paper has to be a little bit longer than it was for the right cylinder because of that. However, it's still going to be 2 pi times the radius, because it's still got to wrap around the full circle. The only difference is that the height rather, changes. All right, so we'll go ahead and demonstrate that. So for the oblique cylinder, we have that it's two circles plus the 2 pi RL. All right, so what about prisms? Now for prisms, you want to identify the shape of each of the faces and use the corresponding area formula. So you have, for this triangular prism, you have two triangles. So you're going to add the area, you're going to find the area of the triangle and then double it, because you have two triangles here. You also have rectangles, right? You have one rectangle here, the one on the bottom, and then the one on the left on the back. That's 3 rectangles. All right, so you find the areas of each of those shapes and then you add them. So for the triangular prism, you have 3 rectangles and then you have 2 triangles. Remember that the formula for the area of a triangle is 1/2 base times height. Formula for area of rectangle is base times height. Now on the bottom, you have a trapezoidal prism. So you have 2 trapezoids here. So we have our 2 trapezoids and we have 4 rectangles. One on the top, one on the bottom, one up to, and 2 on each side. All right, so here's the formulas. So for the formula for the area of a rectangle is BH. Formula for a trapezoid is the sum of the bases times the height divided by 2. All right, so let's go ahead and look at the example of the trapezoidal prism. So if I wanted to find the surface area, I need to add the 2 trapezoids, right? So let's go ahead and add the 2 trapezoids. Now the area of a trapezoid is, so let's go ahead and do that. So let's do the area for the trapezoid. So the area of a trapezoid is 1/2 times the height. The height is 2, times the sum of its bases. So the bases are, in this case, 5 plus 8. And then half of 2 is just 1, and then we have 5 plus 8 is 13. And of course we have 2 trapezoids, so I'll double it, right? So we have 2 of them. Now let's do the area of the rectangle. So let's go ahead and do the surface area in total. We'll get the final answer for this. So the surface area, let's see here. The surface area equals, we have the trapezoid, there's 2 of them, plus, then we have the rectangles. So for this rectangle, we have 5, the dimensions are 5 for this, for the base, or for the height of this rectangle, and 12 for the base. So it's 5 times 12. All right, so now for the rectangle on the bottom, the floor, we have that the height is 8, that the base is 12. So it's an 8 by 12 rectangle. All right, 12 by 8. And then we have the one, so we did the one on top, we did the one on bottom. Let's do the one on the right. So we have a 12 by 3 rectangle here. And we also have a 12 by 3 on the other side. So there's 2 of them. So I'll go ahead and add the other one. All right, and you go ahead and add the surface area. So I'm going to go ahead and add those numbers together. So we got 26 for the first part, plus 60 for 5 times 12, plus 96 for the third part, plus 36, plus another 36. So you should get the surface area is about 254 inches squared. Now for the cylinder on the right, we have that the surface area is 2 pi r squared plus 2 pi rh. So we have 2 pi times radius squared, and so it's going to be 3 squared, plus 2 pi times 3 times 5. So we got 2 pi times 9. 9 times 2 is 18, so we have 18 pi plus 5 times 3 is 15, times 2 is 30. So we got 30 pi. Add those pi's together, we get 48 pi. And of course you can convert that to a decimal. You could do 48 times pi to get your answer as a decimal. All right, so let's look at one more example. This time we have a composite solid. A composite solid consists of 2 or more shapes or solids. So we want to find the volume and surface area. So if we want to find the volume, let's do that first. If I want to do the volume, well, I need to find the volume of the cylinder and then find the volume of the prism and then add them together. So let's find the volume of the cylinder first. The volume of the cylinder, we said, is pi r squared times h. So we have pi times the radius. The radius is 4. And the height of the cylinder is also going to be 4. So we have pi times 4 squared times 4, which is 64 pi. All right, so now let's do the volume of the prism. In this case, this rectangular prism. So the base of this rectangular prism is this here, which is also on the bottom. It's a 6 by 12. So the base is 6 times 12, and the height is 14. So we multiply that by 14. All right, so we got 6 times 12 times 14, and that's 1008. So we can find the total volume by adding the 2 individual volumes. And of course you can get that as a decimal on the calculator, but I will leave it like that. Part B, surface area of the solid. So if I wanted to do surface area, I need to make sure that I do everything correctly as far as surfaces. So we got this surface here, and notice I'm not going to look at this surface because that's actually covered. That's actually not going to be, that's not a surface that I'm going to cover. I'm only going to cover the top part of the cylinder, this, and then around the cylinder. And then I'm going to cover the top part here, the one on the right, part of the one on the front, the one on the bottom, and then the one in the back. Okay, so I'm going to cover this circle. So the surface area is, so if I cover that circle, that's pi r squared. The radius is 4, so it's pi times 4 squared. All right. Now I want to cover this part around the cylinder. And the part, remember that part of the cylinder is 2 pi times the radius times the height. And the radius is 4, the height is 4. Okay, so that takes care of the cylinder. That entire part is the cylinder. Now let's take care of the prism. So for this top rectangle, that's a 6 by 12, so 6 times 12. Same thing for the bottom rectangle, 6 times 12. So I'm going to go ahead and say that there's 2 of them, so I'm going to double that number. And that takes care of the top and the bottom. All right, those are done. The one on the right and the left, let's do that next. Well, that's a 6 by 14, and there's 2 of them. So 2 times 6 times 14. All right, that takes care of that. Now let's do the one on the back, right here. The one on the right, I mean, right back. That's a, that right there is a 12 by 14 rectangle, and there's one of those. The reason why I say there's one of those is because even though there's another one on the front, that one is a little bit more complicated. Okay, so to do the one on the front here, on the left, well, that's a 12 by 14 rectangle, but I have to subtract this circle because I'm not covering the entire surface, right? I'm only covering the part outside of that circle. So I got to do a 12 by 14 minus that circle there. Okay, so it's going to be 12. So I'm going to put this in brackets here. It's going to be 12 times 14 minus, and then that area, which is pi times 4 squared. All right, so we're gonna go ahead. I'm gonna clean this up a little bit. So we got 4 squared is 16, so that's 16 pi. This is 16 times 2, which is 32. So 16 pi plus 32, which is 48 pi. Okay, so that takes care of that part. We got 2 times 6 times 12 is 144. And then we got 2 times 6 times 14. So we'll go ahead and add these all of this together. So we got 2 times 6 times 12 plus 2 times 6 times 14. And that's going to be, and then plus 12 times 14 is 480. And then we'll do, so 480 takes care of all of that. 480 plus 12 times 14 is 648. And then of course we have this minus 16 pi from here. So we'll go ahead and do that. 48 minus 16 is 32 pi. So about 32 pi plus 648. And that's going to be in feet squared. And so there's your surface area. You can get that as a decimal by plugging in for pi. All right, that's going to do it for the video, guys. I hope you found this useful. Hope you learned a few things. As usual, I'll see you in the next one.